In this presentation, we want to discuss speed testing. When we think about speed testing, we want to capture all the relevant movement qualities that could be important for sport, specifically looking at linear and multidirectional speed considerations. Therefore, we're going to provide some top-level tests that give you an understanding of how to categorize and bucket the athletes within the context of linear sprinting, as well as change of direction and reactive agility. Three major objectives. Number one, describe the importance of sprint testing and discuss how to effectively select sprint splits. If you want to start actually looking at how to categorize your athletes across starts, acceleration, which we also call transition, and absolute speed, we need to make sure we select the correct total distance and map the correct splits within that total distance so we understand the actual sprint qualities we're assessing. From there, we want to contrast different timing systems and discuss the importance of reliability. When you're testing both linear speed as well as multidirectional speed, we have to start to take into consideration the timing system that we're using. Therefore, we want to give you a categorization of all the different types of timing systems and how they affect reliability. And finally, we want to describe the importance of agility testing and discuss how to bucket athletes based on non-reactive and reactive qualities. If you reference back both to your linear speed as well as multidirectional speed presentation, we map out how important it is to categorize acceleration and absolute speed, non-reactive and reactive. These tests should give you the capacity to do that, therefore informing your actual movement skill development process. Let's start by looking at the sprint profile. Within the sprint profile, there are three major factors that we want to consider. Number one, we know that linear movement is fundamental to sport, with the distance run dictating the strength and movement needs. Therefore, if you want to specifically look at starts versus that secondary acceleration that we call transition or absolute speed, that directly affects the total distance. Hence the reason we use a 40-yard model, because it allows us to capture each of those sprint splits and make a commentary on those qualities and map those back to strength. From there, we know that Brown et al. Recommends that various sprinting splits be captured to create a correct sprint profile. You could have 10 athletes that all play the exact same sport, but maybe potentially different positions. Some of them might need to spend a bit more time on the acceleration phase of sprinting, whereas others might need to spend a bit more time on absolute speed. At the end of the day, we know we're time limited, especially with athletic populations. So sprint testing, as well as our agility testing, should allow you to prioritize the training process. Then finally, research has shown that different sprint zones involve distinct motor abilities and therefore different strength needs. Hence the reason, if we're just capturing a 40-yard split, we're not getting the totality of the underpinning sprint qualities. Hence the reason timing systems are so important. Now, when we look at our overall timing, we have a multitude of opportunities here in terms of how we run our actual tests. Therefore, we want to remind you of what the overall sprint profile looks like and then go through some options on how you can actually collect your sprinting data based on potentially different sport indicators. So, if you recall back to linear speed, we utilize 40 total yards. And we're typically, as a baseline, going to have those splits set at each of those 10-yard marks. But we know if we want to get a bit more granularity around the start, therefore the first three steps, we could even have a timing gate at that 5-yard mark if you'd like. Now within this, 0 to 10 tells us about our first zone of acceleration. From 10 to 20 is our second zone of acceleration. Anything past 20, we know starts to give us an understanding of overall absolute speed. But as we referenced, not all populations are going to be in the absolute speed zone for the entire 20 to 40 yards. What that means is certain populations, especially untrained or high school athletes, can actually slow down between 30 and 40 yards. With some populations, you're also capturing speed endurance within the capacity of the 40-yard test. Now, to take that back out, we know that that first 20 yards is, again, the overall acceleration zone. And that last 20 yards, within the context of a 40, is the absolute speed zone. Specifically, as a reminder, we broke it up where those first three steps are considered the start because they have a distinct motor ability that is slightly different than all subsequent steps. Past that third step, we really talk about that transition zone of acceleration or secondary acceleration happening upwards of 11 to 12 steps in, typically terminating around 20 yards. And then finally, absolute speed is over 11 steps typically, and their speed from a velocity perspective definitely is over 80% of total max velocity. So if I can at least capture these three zones, I can create a nice commentary on the overall sprint capacities of the athletes that I'm working with. Now, the first way I can capture that data is utilizing a flying start. What you'll notice with all these different types of testing, we are either going to use electric, or some level of hand electric, means there's some level of human influence. And at the end of the day, we are trying to mitigate as much human influence in timing as possible for the simple reason that we know humans have limitations in their reaction time. Oftentimes, a human-based start or a human-based start and finish, which is the case with a stopwatch, can carry errors as much as 0.2 to 0.3. And if we imagine 0.2 to 0.3 might be the improvement we're actually looking for over an 8-week time period. So that's your level of error. We know that's something that we want to mitigate. Hence the reason timing systems allow us to do that. The first way that we can utilize a timing system is what we call a flying start. And a flying start does use a laser approach, which means the system starts and ends with a laser timing system, and each subsequent split within, in this case, the 40, also is laser-based. So you know there is zero human influence. Now, within this, what are we looking at? Well, oftentimes an athlete is going to be 1 meter to 1 yard offset from the first timing gate. Hence the reason it's flying, because they're going to be able to take at least one step before they get into that gate. The reason we typically offset them is because in this test type, they're going to be coming out of a 2-point start. Hence the reason this is commonly used in soccer. And if you look at the soccer literature, they typically use a 1 meter offset, and it's a 30-meter total sprint. So again, while we're sharing 40 yards, are there capacities to test at shorter or longer distances? Yes, but this is still how you'd execute the actual timing. So the way it would work is the athlete starts on the overall line, 1 yard to 1 meter off. Once they start sprinting forward, the second they get into that first gate, time is going to start. From there, each subsequent step, they'll sprint forward, and as they pass each of our gates, again set at 10 yards, that'll give us a split. Therefore, we get these digestible 10-yard splits, and we can aggregate those to look at any total split we want, ending obviously with our largest one being from 0 to 40. Once they pass that final gate, then we have captured all subsequent splits as well as the overall 40-yard dash time. Reminding yourself that if you want a bit more information about start capacities, that you may want that second gate, therefore the first split, to be roughly at 2.5 to 5 yards from the entry gate. The second way that we can assess this is utilizing what we call a beam start. And a beam start is much more common in American football or athletes that need to be in a 3-point stance. Now, there are two different ways you can do this with most conventional systems. You can either start in the beam, where the body actually breaks the beam. Once the body has broken the beam, the system is armed. And the second the body leaves the beam, that's when the time starts. The issue with this is if the beam is in the middle of the body and I start moving forward, I'm going to be able to get at least a little bit of velocity forward before the system actually starts. Therefore, most timing systems utilize what is called a mat start. The mat is a tiny rectangular piece that has a long cord. That long cord hooks into the actual timing gate that is put on the ground on the start line. They would then put their hand on that. By putting their hand on that rectangle, it arms the system. And the second the pressure is off that little mat, that's what starts the system. Therefore, if I'm in a 3-point stance, one of the first things that's going to happen is my arms are going to move. Therefore, we typically get a more accurate start time. So, like the previous, this is still a beam-to-beam or laser-to-laser start type. There is zero human influence. Now, can the athlete try to trick the system where they almost sprint forward, falling if you would, without taking their hand off? Yes, but the reality is if an athlete was to do this, they're not going to optimize their technique. Therefore, it would not be in their benefit. So this can be an accurate way. And most youth combines nowadays are utilizing this mat-based laser start, taking out all human influence. So you'll have the athlete get on the start line. Hand is going to compress on our trigger. Once the hand is removed off the trigger, time starts. The athlete will sprint forward, and again, each subsequent gate that they pass, based on the splits that you've identified, we will get a timestamp until they finish all the way through the final gate, in this case, 40 yards. So in looking at this, again, we have laser, high accuracy. The variability is only going to come within the athlete. Therefore, if you're teaching consistent start methods, they're used to utilizing this mat-based start, you should get reliable results. From there, then, a similar start type is what we call a manual start electronic finish. So it's a hand start electric finish. This is commonly seen in the pro football combine. Therefore, many American football-based combines still utilize this method, but fortunately, we're starting to see it phased out, and more often, they're using the previous method, as we showed, beam-based mat to laser. But in this case, here's what we find. The coach is the person that starts the timer on the first movement of the athlete, opposed to the athlete instigating the start themselves. Therefore, imagine the athlete's on the start line. The coach is sitting parallel to the athlete. They have a trigger whereby the first movement of the athlete, that trigger gets hit, that starts the timing system, and then the athlete will subsequently run, finishing through each of the splits, and then obviously the final split, being at the 40 yards, stops the time. So it's a hand start electronic finish. Is there error still involved in this? 100% there is, because human reaction time visually is still going to be about 0.14 to 0.12 at best. So from an error perspective, you're still going to see a 0.1 advantage on the side of the athlete. Therefore, if you have a very consistent starter, you still can probably get reliability, but you're opening yourself up for much more variability across your athletes utilizing a human-based starting system. Therefore, here's how it looks. Athlete, it's on the start line, 3-point stance. More often than not, the coach is linking in on that tarp arm because that's the arm that's going to move first. Therefore, when that movement occurs, the timing system starts through the activation of the coach hitting the button. The athlete sprints forward. And again, it is a laser split for each subsequent split that you have laid out, finishing with that 40. So is this still better than utilizing a stopwatch? 100%. But nowadays, when you buy any conventional timing system, they're going to give you the mat-based start option. Therefore, utilize that over the hand start if you can. The final way to go through this is obviously a manual stopwatch. With the manual stopwatch, we have a couple issues. Number one, we can't get splits. In that if I'm going to do this, I'm going to have a person either at the 40, at the 30, at the 20, at the 10. So if I had 4 different timers in that case, I could potentially get variability through 4 different people on top of the variability across the athletes with human reaction time. So as we'll discuss in the practicals, can you use a stopwatch to monitor within the context of training? 100%. But do you want to use a stopwatch for your official timing? No. Why? Because the actual variability in the stopwatch can be as high as 0.3. Well, the reality is, in our Pro Football Combine development, our average improvements from hand start to electric, which is exactly how they do it at the Pro Football Combine, so we need to mimic it, is typically 0.22. Well, the fact of the matter is, if we were using a stopwatch to do all of our timing, we could see the error be higher than the actual improvement, or I could falsify an improvement by hitting that too early. Therefore, we want to mitigate use of stopwatches when at all possible, but if you have to use it, try to use it with the same person who consistently uses the same mark by which they start the timer and stop the timer. And we go over exactly how to do this in the practical. So very simply put, the coach is typically going to be on the 40-yard line if they're assigning or testing a 40. The second the athlete starts to move, the timer starts. We're not going to be able to get any subsequent splits. So very simply put, the coach is going to wait for the athlete to come across, and the second, hopefully, the center mass of the athlete crosses the eye line of the coach, that final stopwatch is going to be hit again, giving us the total 40-yard time. We could do this, obviously, at each subsequent split, but you're opening yourself up for high levels of variability. So in looking at this, we gave you 3 different options. Likely the flying start is going to be much better for any athletes that are more attuned to doing 2-point or are on both feet, whereas the 3-point start is going to be much better for any athletes that have to obviously get in a 3-point start or work in a ground-based game where they have to get up and down. So sports like rugby, American football, all typically want to go through a 3-point start. Now, assuming that you can get a timing system, what are the timing considerations that you want to factor in with your purchase? Well, we typically see 3 different systems: single beam system, dual beam system, and signal processing systems. And there's a ton of quality research coming out of Australia on the efficacy, validity, and reliability of all 3 of these. So you can read a lot more on that. Let's start, though, with the single beam system. So only a single beam needs to be broken for the system to start, stop, or mark a split. So in looking at this, imagine I'm sprinting forward. I'm accelerating at that strong 45 degree. As I come up on that gate, let's say my arm is the first thing to pass that gate. Well, theoretically, based on a single beam system, my arm could trigger it. Then what happens? My body follows through, and theoretically, my arm could also cross that gate. But it is only going to get set off or mark a split based on that first run through. Now think about that. If we want consistency, sometimes they might hit it with their arm. Other times they might hit it with their body. Therefore, are you opening yourself up for variability using a single beam system? Definitely. The reality is the speeds that most athletes are moving, a single beam system is still far better than a stopwatch. But if you can, we want to work down the chain to get a system that's a bit more reliable and therefore has fail-proofs within there to make sure you're consistently capturing the body. That then brings up a dual beam system. With a dual beam system, two beams need to be simultaneously broken for the system to start, stop, or mark a split. Therefore, now imagine these systems are a little bit taller. They have two beams coming out. Therefore, as I'm crossing, imagine my arm in this case, again, is the first thing to go through. Well, the fact of the matter is, my arm is going to cross one beam and then the second beam, but it's not going to break them at the same time. Therefore, the only mass big enough to break both beams at the same time would actually be the torso. So in this case, you're much more likely to get a consistent torso break across all of your sprint splits, giving you increased reliability across the sprint splits and the total distances. Some timing systems have gone to such great lengths that they use a triple beam system. This probably is overkill. Now the final one is actually the one that we use here at Exos, and that is a signal processing system. And we specifically use the Fusion Sport Smart Speed system to do this. And this has been compared to the dual beam in terms of its reliability. So either way, you're probably having great reliability with dual beam or signal processing systems. So with signal processing, here's what happens. The beam break signal is recorded to identify how many times the beam was broken and for how long. Specifically then, the algorithms in Smart Speed factor in this, that the longest beam break, representing typically the torso, will be used to start, stop, or mark a split within the system. Therefore, if I'm running, it knows one beam break, first arm, second beam break, body, third beam break, arm. So literally in the system, it would have those three beam breaks. And it would also know how long the beam was broken. Well, obviously, the torso is going to be thicker than the arm, so it factors that, and it takes the center point of that beam break. So the fact of the matter is, it not only factors in what beams are being broken, but for how long, to get even more accuracy in the timing. Hence the reason when you're dealing with decimal places, 1 or 2, so 0.2 or in some cases 0.05 improvements to the hundredth, you want to make sure you have accuracy and reliability. Otherwise, your change could be fogged through inaccuracy or it could be inflated due to inaccuracy. And we want to make sure we're always accurate with our timing, especially if you're working with people preparing for the Pro Football Combine. So factor in all these conditions. Nowadays, this should be on your wish list from affordability perspective and budgeting to make sure you buy a timing system, because they're not only used for linear speed, they're also used for all of our multi-directional speed. So in final here, let's do a quick little check for learning. Number 1, write down 3 to 5 sentences discussing the importance of the selected distance and splits relative to sprint qualities and sport specificity. Simply evaluate and review how different sprint splits effectively map to our different sprint qualities and how those relate to different sport-specific demands. Then number 2, contrast how different timing setups and timing systems in terms of dual beam, signal processing, and signal beam can be used based on desired validity, reliability, and specificity, giving yourself the best opportunity to maximize the reliability of your timing sessions.